IPoDWDM IP over dense wavelength division multiplexing, is a networking architecture that integrates IP routing equipment directly with optical transport systems. By embedding advanced optical transceivers known as coherent pluggables directly into router ports, IPoDWDM eliminates the need for separate, bulky transport hardware. In the past, IP and optical were two distinct worlds managed by different teams and different equipment. IPoDWDM collapses these layers into a single, streamlined system. How IPoDWDM changes the architecture in a traditional network: a router uses gray, short-reach, optics to connect to a standalone transponder or muxponder. This transponder then converts the signal into a colored, DWDM, wavelength to travel across the long-haul fiber. Component traditional architecture IPoDWDM architecture coherent colored pluggables, example optics short-reach gray optics 400ZR, intermediate standalone transponders / eliminated, integrated into router, hardware muxponders management separate IP and optical NMS unified / converged management footprint high, multiple chassis / racks, low, router only. Its role in the modern network as of 2026, IPoDWDM has moved from a niche technology to a core strategy for hyperscalers and telecommunications providers. Its role is defined by four major shifts: 1. Delayering and cost efficiency. By removing the transponder layer, operators see massive reductions in capex, less equipment to buy, and OPEX, less power, cooling, and floor space. Modern 400ZR and 800ZR pluggables allow a single router port to send data hundreds of kilometers without any external transport boxes. 2. Supporting 5G and edge computing. 5G requires ultra-low latency and massive bandwidth at the edge of the network. IPoDWDM allows service providers to deploy high-capacity 100G or 400G links directly from small edge routers, making it economically viable to bring high-speed fiber deeper into residential and industrial areas. 3. Data center interconnect, DCI. Hyperscalers, like Google, Meta, and AWS, use IPoDWDM to link massive data centers within a metro area. Because these facilities often sit 40 to 120 kilometers apart, the ability to plug a DWDM module directly into a switch and hit the fiber immediately is the most efficient way to scale east-west traffic. 4. Unified automation. Modern networks are increasingly software-defined, SDN. IPoDWDM allows the router's operating system to see the optical layer. This enables multi-layer restoration. If a fiber is cut, the router can immediately detect the optical failure and reroute traffic at the IP layer in milliseconds, often more efficiently than traditional optical switching. Key enabling technologies: coherent pluggables, 400ZR/ZR plus the magic miniaturized chips that fit a long-haul transponder's power into a module the size of a thumb drive. Open line systems, OLS decoupled optical amplifiers and filters that allow routers from one vendor to work over optical fiber managed by another. To understand the difference, it's helpful to see how traffic travels in a traditional setup versus the modern IPoDWDM approach. In a traditional network, the IP and optical layers are physically separated by multiple cables and devices. Example, a packet's journey. Traditional architecture: imagine a customer is sending data from a data center in New York to one in New Jersey. 1. At the IP/MPLS router, New York, packet handling. The router receives the customer's data, determines the destination, and attaches an MPLS label for fast switching. The gray handoff: the router sends the signal out of a standard Ethernet port using a gray, short-reach, 1310 nanometers, optical transceiver. This signal can only travel about 2 km, 10 km. 2. At the DWDM transponder, New York, optical conversion. The gray signal enters a standalone transponder, part of the DWDM shelf. Mapping and wrapping: the transponder converts the electrical signal back to light and wraps it in an OTN, optical transport network, frame for error correction, FEC. Coloring: most importantly, it changes the wavelength to a specific color, example 1550.12 nanometers, on the ITU grid so it can be multiplexed with dozens of other channels on a single fiber. 3. Through the fiber core. The colored wavelength travels across the long-haul fiber, passing through amplifiers and ROADMs, reconfigurable optical add-drop multiplexers, that keep the light signal strong and directed. 4. At the destination, New Jersey, demultiplexing. The DWDM system at the New Jersey side picks out the specific wavelength. Handoff: the New Jersey transponder converts the colored long-haul light back into a gray signal. Arrival: the signal enters the New Jersey IP/MPLS router, which strips the MPLS label and delivers the original packet to the customer. The IPoDWDM comparison. In a modern IPoDWDM setup, the middle step is removed. The router uses a coherent pluggable, like a 400ZR. The router does the coloring itself. The packet goes from the router's internal switch fabric directly onto the long-haul fiber as a colored wavelength. Benefit: you eliminate the transponder hardware entirely, reducing the number of optical to electrical conversions and saving significant power. Advantages of IPoDWDM. The advantages of IPoDWDM stem from the convergence of two previously separate worlds. By moving the optical intelligence into the router, operators change the economics and the physics of the network. Here is a summary of the primary advantages. 1. Massive cost reduction, CAPEX and OPEX. This is the most immediate driver for adoption. Elimination of transponders. By removing the standalone transponder shelf, you eliminate the need for gray optics on the router and the transponder itself. Reduced power and cooling. Fewer hardware chassis mean significantly lower electricity bills and less heat generated in the data center. Space savings. In crowded urban point of presence, POP, locations, saving a few racks of equipment can prevent the need for expensive facility expansions. 2. Simplified network architecture. Traditional networks have a layered complexity that IPoDWDM flattens. Fewer points of failure. Every patch cable between a router and a transponder is a potential failure point. IPoDWDM removes these interconnects. Lower latency. By reducing the number of optical-electrical OEO conversions, signal processing time is minimized, which is critical for high-frequency trading and real-time AI applications. 3. Unified management and automation. In a legacy setup, the IP team and the optical team often use different software tools. Single pane of glass. With IPoDWDM, the router's control plane can monitor optical health, like signal-to-noise ratio or chromatic dispersion, directly. Faster provisioning. New capacity can be turned up via a single software command rather than coordinating manual cabling between two different hardware platforms. Multi-layer restoration. If a fiber is cut, the router can immediately trigger IP-level rerouting because it has direct visibility into the physical layer failure. 4. Scalability. For the 400G/800G era, as traffic grows, the traditional model becomes physically unsustainable. Standardization. The shift towards standardized pluggable modules, like QSFP-DD, ensures that routers from different vendors can work over the same optical line systems. Density. Modern high-density routers can host 36 or more 400G DWDM ports in a single rack unit, RU, providing massive throughput that would have required multiple rooms of equipment a decade ago. Summary table. Feature. Traditional DWDM. IPoDWDM hardware footprint large, separate chassis, minimal, integrated pluggables, interconnects many, gray fiber patches, none, internal to router, power consumption high, W/Gbps, low, W/Gbps, control plane fragmented unified, SDN ready. Key technologies in IPoDWDM.